Okay, so it is 11, so let us start. Okay, so we were discussing continuous time Fourier transform properties yesterday. Not properties. So let's continue with that discussion. Today we will see few more properties and few more examples also. Yeah, this is a revision for most of you, but yeah, hopefully some things will be new to you. Okay, so we ended this Fourier transform of sine function, which is not square integrable. So yeah, we defined it in the limit like this. Okay, so yeah, this is where we ended yesterday. So let's continue from then onwards. We also did a bit of linear algebraic interpretation of signals and systems, transforms and so forth. I forgot to mention this one property. So maybe I will start with that and then we will continue with this example. Okay. So yeah, this is the eigenvector eigenvalue interpretation which I forgot to mention yesterday. So you guys, I don't know whether you have seen this before or not, but yeah, if you have not, then let me refresh you or yeah, let you know about the eigenvalue and eigenvector interpretation for finite dimensional vector spaces or matrices. Okay, so A is our matrix, square matrix n cross n. Then we say that V1 is an eigenvector of A if A times V1 is lambda 1 times V1, where V1 is non-zero. Okay. Lambda 1 could be 0 or non-zero, but okay, so there was some issue with network, so I'm back now. Yeah, as I was saying, so this is an eigenvalue equation, this one. V1 is an eigenvector and lambda 1 is an eigenvalue. V1 is non-zero. So this is another eigenvalue equation. So V1 and V2 are distinct. Okay, V1 is not equal to V2. Lambda 1 and lambda 2 could be same, distinct. Doesn't matter. So in general, you can have multiple eigenvectors and multiple eigenvalues. So if A is n cross n, then there are n number of eigenvalues, but you may not have n eigenvectors always. Okay, but we will not get into those complications. Suppose there are n eigenvectors. Yeah. To start with, let's just take these two eigenvectors, V1 and V2. So if we put these two eigenvectors in one matrix, okay, so the first column of this matrix, this one on the right hand side is V1 and the second column is V2, okay, and we have these two equations at the top, and you can check that this this equation holds, okay. So we know that A times V1 is lambda 1 V1 and A times V2 is lambda 2 V2, okay. So A matrix times this n cross 2 matrix gives you this. Okay, so this is n cross 2 and this is 2 cross 2. So you can check this. Okay. I will not try to show this. This is a simple, straightforward manipulation. Just simple matrix algebra. So instead of just two eigenvectors, if I know that my matrix has n independent eigenvectors, so they form n columns of this square matrix capital V, then we get this equation. AV is equal to V times D, where D is a diagonal matrix which has all eigenvalues on its diagonal. And from that we can always write this equation. Okay. So provided A is diagonalizable. So not all matrices are diagonalizable, but yeah, almost all of them are. So there are some complications like Jordan forms and so on, which we won't get into. But yeah, provided that there are n independent eigenvectors, you can always diagonalize any matrix using its eigenvectors, and this is basically change of basis. Okay, so we are taking a new basis. So yesterday we saw, right, the coordinates change when we take different bases. Okay. So just like that, the matrix entries will change if we change the underlying basis. Okay. So yeah, you can interpret it like that, or you can also interpret it as diagonalizing a matrix. So taking this idea a little forward, uh, yeah. So we can interpret these exponentials as follows. Okay. So if you have any linear time invariant system, so this is not an arbitrary system. This is a very specific linear time invariant system. Okay. H is its impulse response, and if you give this as its input, then it turns out that you get this as its output. So that, yeah. Any question? This follows from the convolution equation. So y of t is not, again there was some. So you just do this integral h of tau, let me write, and e to the power j omega t minus tau d tau. If you simplify this, you will get this expression. And similarly, if you feed in a complex exponential with a non-zero real part, you get this equation that follows from Laplace transform definition, but yeah, we will see that later. So at least you can see an eigenvalue eigenvector relation in here. So this is your linear time invariant operator, which is an equivalent of this finite dimensional matrix which we had here. This function is serving like an eigenfunction to this infinite dimensional system, and what we get as its output is just some complex number times this same function. Okay. So these complex exponentials are eigenfunctions of this LTI system. For any LTI system, they serve as eigenfunctions. And when what we do when we take Fourier transform is basically we are changing the basis from the Dirac delta basis to this complex exponential basis, and yeah, these are the sort of diagonal entries which we had here. So lambda 1, lambda 2. Instead of that, we have this Fourier transform entries as the diagonal entries. So yeah, when we change the basis with respect to eigenvector basis, we diagonalize a matrix, and this is what is going on underneath when we take Fourier transforms of LTI systems. Okay, so previously we looked at signals and their Fourier transforms and how it is related to the change of basis. Now we are looking at systems and the interpretation of Fourier transform of a system. Yeah. So the interpretation is, yeah, because these serve as eigenfunctions, you sort of diagonalize your system by changing your basis from Dirac delta to this. Yeah. So these are the eigenvalues of your system. So again, if you uh, don't understand every bit of that, it's totally all right. But if you do understand it, it just gives you an alternate way to look at these things and appreciate what is going underneath these things. Okay. So we will see one of the properties of Fourier transform, which turns convolutions into multiplication. So that can be interpreted in terms of yeah, this diagonalization and so on. So I will uh, come back to this point when we look at convolution multiplication property. Okay. So another advantage of using a different basis is Yeah, it brings out some features in your. So if you are analyzing some signal, it may bring out different features of your signal, and if you are analyzing data, then yes, it may bring out some different features of your data. So for example, when you are decomposing your signal in terms of this complex exponentials, you can see how many high frequency components are there, how many low frequency components are there, and things like that, which is not apparent from the time domain representation. Yeah. So this idea is basically prevalent. So this is just a philosophical statement I'm making. So basis vectors are basically building blocks. Okay, so every vector like we saw here can be represented uniquely in terms of this basis vector. So yeah, in that sense they are quote unquote building blocks, and different building blocks, so different set of bases can bring out different features in your signal or whatever data you are analyzing. So yes, this theme you will see repeating again and again. Okay, if you study some sort of data data processing or data analysis, yeah, this theme you will keep encountering. And yeah, sometimes in literature these things are also called atoms. So yeah, that this term comes from uh, that physics interpretation of decomposing molecules in terms of atoms. So yeah, atoms are not indecomposable in the strict sense, but yeah, you get what this means. Okay, so enough of that. Let me continue with yeah, these examples. Okay, so let me finish unit step, which is a straightforward consequence of Fourier transform of sine function. Then let us go to inverse Fourier transform of sinc function. Okay, so yesterday we saw that rect function. Where was it? Yeah, so Fourier transform of rect function is a sinc function, and today let us see that the inverse Fourier transform of the sinc function gives you rect function. And then we can move on to properties and so on. All right. So deriving unit step is straightforward. So unit step signal, you can write unit step as the sine function plus the constant function, and then you put in the half factor. Okay. So the for t strictly less than 0, you just get 0 here because sine is -1 and you are adding +1 in here. And for t greater than or equal to 0, you have 1 plus 1, 2, and then to get rid of that 2, we are adding this half factor. Okay. And now the Fourier transform of step function follows from linearity. Yeah, so we know Fourier transform of sine function, which is 2 over j omega, and yeah, we also know that Fourier transform of 1 is 2 pi times delta omega. Okay, so the 2 factor is cancelled with this half factor, and this is the Fourier transform of unit step. Okay, so I hope that is fine. Okay, so let's now move to the inverse Fourier transform of sinc function. Okay, so let us start with yeah, this formulation of the sinc function. Okay, so I'm going to put this as the expression for xj omega, and we are going to apply the definition for inverse Fourier transform. Yeah, here it is. So this is our x of j omega, the sinc function, and yeah, we are taking inverse Fourier transform of that. Okay, so let's do some simplification first. Let's absorb this in both the exponentials. So here we get t minus capital T1, and here it is t plus capital T1. Okay, so this is straightforward. Now just expand these complex exponentials in terms of sine and cos. is the next step. Now, since odd functions cancel out over the entire real line, if you integrate odd functions, the integral is 0. So odd functions will be, yeah, so this is an odd term, omega, and this is an even function. So cos over omega is an odd function. So this will drop and this term will drop. And J will cancel, okay. So sine over omega, these two terms will survive. Okay. And this integral now, we can just consider integral over 0 to infinity and 2 times that, okay. So this half factor cancels out. Okay. So the negative sign is coming in from here, no negative sign in here.
Excuse me, sir. So we need to first check for convergence, then only the integration will 0.
Right. So yeah, we are assuming that, I mean, we can show that the sinc function is square integrable. That's why this integral makes sense. So yes, I will not try to prove that in the class. Maybe I will after we derive Parseval's theorem. Okay. So let's hold on to that question. Yes, that is absolutely correct. Let me at least show you. If you have seen Parseval's theorem before, then yeah. So I hope you have seen Parseval's theorem before. So xt is square integrable if and only if its Fourier transform is square integrable. That's what Parseval theorem says. Now rect function is square integrable. Okay, that is straightforward. It is of finite duration and it has finite value. And from that it follows that sinc is also square integrable. Okay, so you need square integrability for defining Fourier transform. Sinc is not absolutely integrable, yeah, but square integrability is good enough for us to define this integral. Okay, so I hope that that query gets answered. So these integrals make sense because yeah, this is square integrable from Parseval's theorem. Okay, so continuing, yeah, this simplification. Yeah, so we were at this point. So another bit of manipulation which we are going to do is as follows. So we are going to insert this substitution, yeah, for 1 over omega. Okay, so for 1 over omega, we are going to substitute this term. So you can easily check that this is valid by doing this integration. Okay, again I lost the connection for a bit, but yeah, now I'm back. Yeah. Okay, so you insert this expression in here. So you have two integrals now and this additional term. Okay. All right. So another formula. So sin ax times e to the power minus sx evaluates to this integral. This is actually the Laplace transform of sin ax. Okay, but you can take this as a standard integral. Okay, so we are going to substitute this upstairs. Yeah. So both the integrals, we are simplifying one integration in each of these integrals. Okay. So this is our a t minus t1 and yeah. So 31 follows from yeah, this formula. Okay, and now we are almost there. So let's substitute a for this t minus t1 term. Okay, so this we can rewrite as a over a squared plus s squared, and doing further simplifications we can write it like this. Okay, so 1 over a times mod a and yeah, this times d1. So again, mod a over a turns out to be sine of a. You can easily check that. And this is tan inverse of y, yeah, and evaluated at the limit gives you pi by 2. Okay, so inserting this upstairs gives us this expression. So 1 over pi times pi by 2, so pi and pi cancel, and sine of t1 minus t and sine of t1 plus, let me draw this. Uh, so yeah, sine of t plus t1, this looks like this. Okay, so this is minus t1. This is sine of this is sine of t plus t1. This one, and yeah, I'm getting a bit confused. Sine of t minus t1 will start from here. Yeah, let me not draw that. Okay, I'll make a mess of it. But yeah, you can verify that this is the right function. Okay, we can do it offline. If I start doing it in the class, then I'm likely to make mistakes, and let me not do that. Okay, so I leave that as an exercise. If you can't show that, then yeah, we will do it sometime later after the class time. Okay, so that is the derivation of inverse Fourier transform of sinc function, which is the rect function. Okay, let me also do this one, and then we can go on to properties, or maybe we can start with properties first. So let me not do all properties. Some of them are pretty straightforward, and you have already seen that. So yeah, time shift. The only thing is, yeah, you need to show it both ways. Okay, so if you do time shift here, this is what you get as its Fourier transform, and yeah, the inverse Fourier transform of this is the shifted time signal, like that. So this first few, let me not do it because yeah, you have already seen this, and you can just read it, and the derivations are pretty straightforward. So let's make note of this. What is the Fourier transform of cosine function? Similarly, you can obtain an expression for Fourier transform of sine function. Yeah, so cosine is yeah, half of sum of these exponentials, and we know this frequency shift property now, and using that, yeah, this is the Fourier transform of cos function. Okay, so it is two delta functions at omega and minus omega, so something like this. So Dirac delta at minus omega and omega naught, and Dirac delta at omega naught. Okay, so this is Fourier transform cos omega t. Conjugation also is straightforward. Time reversal, yeah, these easy things let me skip. Convolution multiplication is also straightforward. Okay, so and yeah, multiplication turns into convolution. You can just use this same simplifications to show that the Fourier transform of multiplying two signals in time domain turns into their convolution in the frequency domain. Okay. So the only difference is there is this factor. Okay. So x of t there is a 1 over 2 pi factor. That is the only difference. X of j omega, let me not write j omega, convolution with y of j omega. So there is 1 over 2 pi factor. That is the only difference. And the derivation is exactly identical. So you can start with 1 over 2 pi x j omega convolution y j omega and show that in time domain you get multiplication and vice versa. But let us go through this modulation property because this is important in communication engineering. Okay. So in analog communication, yeah, you have this sort of modulated signals. Okay. So xt is something you want to transmit, and you multiply xt with this sinusoidal function, this cos omega naught t. Okay, so let me draw this. So suppose x j omega looks like this. So I've drawn this badly, but it is symmetric about it. Okay, so this is my Fourier transform of x, and I've already we have already seen Fourier transform of cos function also, right? So when we do this multiplication, xt times cos omega t, in the Fourier domain, this will turn into convolution. So there is a typo here. This should be half, okay, not pi. I made a mistake. So there is pi times delta function. Yeah. So pi times delta shifted deltas, but as we have seen here, there is a 1 over 2 pi factor when you go from time domain multiplication to frequency domain convolution. So that pi gets cancelled and half stays as it is. So that typo you can rectify. Okay. I will also rectify and upload the corrected version. This should be half, not pi. So when you convolve this with these two impulses, what we get is and there is a half factor. Okay, so magnitude gets scaled by a half. Yeah, so magnitude of this is scaled by half, and instead of this this magnitude spectrum, we have after multiplying it with cosine, we get these two shifted spectrums. So this is convolved with shifted impulses. Okay. All right. So this is what you transmit. Okay. So in analog communication, we multiply this this signal with this cosine function, and yeah, this is what gets transmitted. In time domain, yeah, it may look something else, but yeah, this is what it looks like in the frequency domain. So let's see what happens at the receiver. So receiver receives these two waveforms in the frequency spectrum. So at receiver, we again multiply the received signal by this same function. Okay, so xt times cos omega naught t is yt, and at the receiver, we again multiply yt with the same sinusoid. So this was this is y of j omega. Let me erase this. not write omega naught. And Z now at the receiver end, we are going to do y times cos. So in the frequency domain, capital Z is 1 over 2 pi. Capital Y, convolution with the same impulses. Okay. So we are going to convolve this now. Let me do that on the next page. So this was our y of j omega obtained from x of j omega. Right? X of j omega was this triangle which we convolve with these two impulses to get y of j omega. And now we are going to convolve y of j omega. So remember that there is a half factor in here. So let me write that half in here. The magnitude got scaled by half, and yeah, the spectrum got shifted. So this is minus omega naught, and this is plus omega naught. And this gets convolved with the same impulses again at omega and minus omega naught, and omega naught, and this is minus omega naught. And let's draw zj omega downstairs. Okay. So let's convolve this triangle with these two impulses first. When we convolve this triangle with this Dirac delta function, yeah, we will shift this triangle to minus 2 omega. So I hope that is clear. Yeah, it was already at minus omega naught, and this is getting convolved with a Dirac delta function at minus omega naught. Okay. So this gets shifted by one more omega naught, and there is 1 over 2 pi factor also. So this has magnitude pi and pi. And yeah, draw this as a dotted line. This is 1 over 4. Why it is 1 over 4, let me explain. So this was already half the previous magnitude, and there is 1 over 2 pi factor turning multiplication into convolution. So this pi will get cancelled with this pi, and there is additional half factor. Okay. So this gets scaled to 1/4 now when you convolve this with this. When we convolve this with this, then omega naught and omega naught they will cancel each other, and you will get a spectrum at the origin. Okay. So let me not draw that because there is additional term coming in from this part also. So let us see that additional term right now. So we have seen that this getting convolved with this gives you triangle at the origin. Similarly, this getting convolved with this will give us another same triangle at the origin, and half plus half, sorry, quarter plus quarter will give us 1/2. So this is 1/2, and then this getting convolved with this will give another factor at 2 omega. Sorry, this is badly drawn, but this is 1/4. Okay, so this is our z of j omega. Okay, and now the question is, can we recover x from z? is it possible? So yeah, this is a question for you guys. So maybe you can think it for a few seconds or for some time and yeah, give it a thought. This has connections with sampling theorem and those sort of things, but yes, you can think about this, how to recover x from z. So anyone has any ideas? So this is how z looks like. There are these additional triangles minus 2 omega naught and 2 omega naught, but yeah, we also have this x which is scaled by half, that we can always scale by 2 to recover x as it was. But what to do with these two additional triangles? Can you think of some strategy to get rid of these things? So we have signal z of t. The question is, can we process z of t in some way? Okay, so maybe some LTI system, can we design an LTI system which gives us gives back x of t? Okay. Yes. Any idea?
If we have a rectangle,
Right.
then we can get.
Yes. So yeah, be more specific. Yes, if you can design a rect function. Sorry, this is again badly drawn, but yeah, think of this as a flat line. So somehow, if you can design this system having this frequency response, which we draw that as a dotted line, which only retains this code. Then you can recover x back from there. So we are already seen that this rect function is the Fourier transform of the sinc function. So that means yeah, this filter has to be, impulse response of this filter has to be sinc function. And we will see later that this is actually the low pass filter, ideal low pass filter. This does not exist in practice, but yes, in principle, we will first have a look at this ideal low pass filter and its physical realization. Also, we will see why it is not realizable in practice and so on. But hopefully, you get some idea. Okay, so why rect functions are important, sinc functions are important, and so on.
Sir? Sir, here are we recovering x because the final amplitude is half the initial.
No, you can. Okay, so rect function. This is half of the initial magnitude, right? So you can take rect function to be of magnitude 2, right? So that half factor is immaterial. You get half of xt or you get x of t. That does not matter, right? So even if half of xt omega is Fourier transform of half of x of t. So whether that half is there or not, yeah, it's immaterial, and you can always get rid of it by just scaling either in time or frequency domain.
So here we convolute with rect function to get or recover x.
Sorry, say it again.
We use rect function to recover this.
Yes, right. So
We
rect function in the yeah, say it again.
We convolute with that.
No, not convolution. Okay. Yeah. So we are multiplying with rect function in the frequency domain, right? This is multiplication. If you convolve this waveform with rect, then yeah, you are going to get something complicated. So we are let me write that. So we are multiplying zj omega with omega. Okay. So this is multiplication in frequency domain, which retains just the central lobe. So let me call this lobe, and let me call this side lobe. So if you multiply this Fourier spectrum by the rect function in the frequency domain, it only retains the central lobe and remove these two side lobes. So that is multiplication in the frequency domain, and in the time domain you are doing this z of t. We are convolving with the sinc function. So these two form a Fourier pair and these two form a Fourier pair. So we are convolving zt with sinc function to recover x of t. This is okay. So I hope this is clear.
Yes, sir.
Okay, so yeah, this shows up a lot in communication engineering. Okay, so those who will take communication engineering later, yeah, they will see these things appearing again and again. Okay, so we don't have much time, so let us finish differentiation and integration. Let me see. Okay, so tomorrow definitely I want to finish this. Yeah, so let me quickly do differentiation first. So differentiating in time domain is same as multiplying with j omega in the frequency domain. This is what we want to show. One way is straightforward, other way requires a bit of work. So yeah, one way which is straightforward is as follows. So x of t, you just write x of t as just use the definition of inverse Fourier transform. So x of t is x of j omega times e to the power j omega with 1 over 2 pi factor. And now differentiate on both sides with respect to t. Okay. So this is independent of t, and we differentiate with respect to e, this complex exponential, and that brings out j omega. Okay. So now, yeah, from here you can see the inverse Fourier transform of this j omega times x j omega is d dt of xt. Okay. So yeah, this is what I am saying here. F inverse of this is d dt of xt. So let's now show that Fourier transform of this is this. So the forward way is slightly tricky. So note that x is square integrable. So because its Fourier transform exists, so x must vanish at plus and minus infinity. Okay. So if x does not vanish at plus and minus infinity, it cannot be square integrable. Okay. So we are going to use that property. Yeah. Okay. So let's recall this Leibniz rule first. So yeah, it's just the product rule. So product rule of differentiation. So yeah, this is just that. So let me not explain that. Okay. So this is the expression which we are going to use. Okay. So we know from a definition of Fourier transform that xj omega is xt times e to the power minus j omega t. That's from definition of Fourier transform, and now just multiply both sides by j omega. Okay. And now we are going to use this expression. So j omega, sorry, where was I? Yeah. So let's take this to the left hand side and this to the right hand side. Okay. So that's what we are doing. This term is this term under the integral sign, because we have this integral sign, and this term which we have taken to the right hand side is also under the integral sign. Okay. Now this term, if you evaluate this integral, we get this expression evaluated at two extremes, and this must vanish because x is square integrable and x vanishes at plus and minus infinity. Okay. So this term disappears, and what we get is j omega times x j omega is just this. Okay. So yeah, this is just the Fourier transform of ddt of xt. So that's that. And now you can use this differentiation rule to simplify ODEs. Okay. So any differential equation of any order, so of course linear, time invariant, but yeah. So imagine any differential equation like this. This is your output and this is input. And now using this differentiation rule, you can just apply this repeatedly. Okay, so this is just once differentiation, but yeah, you can multiply it n times, and yeah, this j omega to the power n factor will come out each time. Okay, so this differential equation, you can convert it into an algebraic equation like this. Okay, so q of j omega is just a polynomial in j omega. This is a polynomial in d dt, which gets converted into a polynomial in j omega. Y j omega is Fourier transform of y. Okay, this need not be a polynomial. The q of j omega is a polynomial, and similarly p of j omega is also a polynomial, because this is just a polynomial differential operator, where instead of the differential operator you are substituting j omega. Okay. And now you can find the frequency response like this. So y of j omega is h j omega times x j omega, where h j omega is p over q. Okay. So these two are polynomials. So this is a rational function. And yeah, you know what is the inverse Fourier transform of rational functions. Yeah, use partial fractions and use the exponential property of inverse Fourier transform. Okay, so complex exponentials map to 1 over whatever s j omega plus a or whatever. So you can find impulse response for ODEs, and you can also solve ODEs using this. So ODEs with initial conditions, yes, those ODEs we will see a bit later in Laplace transform, but yeah, ODEs without initial conditions, those so forced responses you can surely find using the Fourier transform technique. Okay, so this is the frequency response. This is the frequency response of your input or the Fourier transform, and you know how to invert Fourier transform, right? So just invert the Fourier transform to find the forced response of your differential equation. Okay. So frequency response is yeah, something like this. So if you are plotting frequency response of h of j omega, then you plot it as follows. On the horizontal axis you have real part of h j omega, and on the on the vertical axis you have imaginary part of h j omega. Okay, so omega goes from minus infinity to plus infinity. So here it is. This is the omega axis, and omega goes from minus infinity to plus infinity. And for each values of omega, you plot h j omega in this plane. Okay, so you can start, let's say, from omega is equal to 0. Maybe it starts from here, and whatever. Maybe it goes on like this, something like that. And so this is the omega going from 0 to plus infinity, and then you can also draw similar plots for omega going from 0 to minus infinity. Okay, so I don't know, maybe something like this. whatever. So minus infinity to 0 will look like this, for example. Okay. So this is the frequency response. Okay, so omega is not explicitly shown in this plane, but yeah, you are tracing this curve as omega goes from minus infinity to plus infinity. Okay. So this is how frequency response looks. So there is also magnitude response and phase response. So instead of writing the frequency response, so h j omega is a complex number. So h problematic writing this every time. So h j omega is magnitude of h. So this is a polar representation, and angle. So some theta. Since this is a complex number, you can write this in this polar form, or e to the power j theta or whatever. Theta is a function of omega, and this is also a function of omega. And now you can plot them separately. So this is, for example, magnitude of h j omega against omega. This is the magnitude response. So I don't know, something like this. Whatever. And this is the angle of h, okay, also called phase response. And I don't know, maybe linear, something like this, against omega. So these terms also you will see repeatedly: magnitude response, phase response, frequency response. So this is what it is. Okay. So we don't have much time. Let me see what I can do. Uh, Let me do integration today. Some of you may have a class at 12, but yeah, let me at least do that. Okay, so this is not integration. This is differentiation in the frequency domain. Okay. So previously we saw differentiation in time domain. So let's quickly see differentiation in the frequency domain. Maybe I can leave this as an exercise. Let me leave that. Let me leave that as an exercise. It follows using similar ideas, and the derivation is given here. Okay, so you can go through that. Let me do the Gaussian example instead. So if we have time tomorrow, I will go through this derivation. Yes, let's take this for granted for now. So differentiation in time domain leads to multiplication in the frequency domain. Okay. So this is our property. Okay. So yeah, you can take this j to the other side also. So we saw that differentiation in time domain gives you a j omega factor in the frequency domain, and likewise differentiation in frequency domain gives us minus j times t factor in the time domain. Okay, so these two properties we are going to use to derive the Fourier transform of a Gaussian function. Okay, so the previous one, yeah, this property, and this property. Okay, so let's at least finish the Fourier transform of Gaussian today. So let me draw that also. This is our Gaussian, let's say, in time domain. So something which has this expression, and let's find out its Fourier transform. Okay, so note that we are going to use the differentiation in time domain as well as differentiation in the frequency domain. So let's differentiate g in time domain first. Okay. So if you do this differentiation explicitly, yeah, this is what you get. Okay. So exponential stays as it is, and yeah, derivative of this 2 factor cancels, and minus t over sigma squared is what you get. Okay. So this is just applying ddt in here. Now, when you apply ddt in time domain, in frequency domain, you have j omega factor. Yeah, from the differentiation in time domain property. Okay. So yeah, this j omega, this term comes from this. Okay. And this term comes from this. So from here you see that multiplication in time domain is differentiation in frequency domain with this j factor. Okay. So in here we have multiplication in time domain with g. Okay. So that will turn into e by d omega in the frequency domain. J factor will be there, and yeah, this minus 1 over sigma squared factor stays. Since these two are equal, these two must be equal. So I hope that is fine. This is related to this, and this is related to this by the differentiation multiplication property. Okay. Now just simplify. So collect terms in gj omega on the one side and terms in d omega on one side. So yeah, this is just that simplification, and then integrate with respect to omega. Omega varying from 0 to small omega. Okay, so on the left hand side you get this factor. On the right hand side we have this. So log of g0, yeah, that is just the area under the curve in the time domain. So that is 1. So this factor is so log g of 0 is 1. So log of that is 0. Okay. So g of j omega is just exponentiating this, taking anti-logs on both sides. So yeah, you get that g of j omega is again a Gaussian. So let me draw that here. The width might be different, but the shape is the same. Okay. Yeah. No, even the width is the same. Or yeah, there is a scale factor, of course, and yeah, there is something. So here we had sigma squared in the denominator, and here it is in the numerator. So of course width is different. So they are reciprocal, and there is a different scale factor also. But yes, it is still a Gaussian. And conversely, yeah, I'm almost out of time, but you can also show converse also, again by using the multiplication and differentiation property of Fourier transform. Okay, so I leave that to you guys to check this. Okay, this should be easy enough to understand. Okay, so sorry for overshooting. Let me stop today's class. I'm here for questions. So yeah, those who want to leave, they can leave. I can take questions, and if you have time, I can finish this derivation also, this minor simplification. But yeah, class is done. So yeah, those who want to leave, they can leave. Thanks for attending.